Greetings everyone, and welcome to my lecture series on sequences and series. So today we're going to look at sigma notation, which is a particular way of writing a series. But before we start, I want to remind you that a sequence is an ordered list of numbers. So for example, we've got the numbers 16, 20, 24, ... all the way up to 72. So this is a finite sequence because it stops somewhere. And you can see that this one has an adding pattern that to get from 20 from 16 we add 4. Similarly, we add 4 to get to 24 from 20. And we stop eventually at the number 72. Now a series is the sum of a sequence. So we take, for example, that previous sequence, and now we're adding up all those numbers in order to get a sum. And the thing to remember is that a series, for a finite series where you've only got a certain amount or a certain number of elements in there, is just going to be a number. We're going to add all of these up and come up with what the sum is. So to do sigma notation, we need to use the Greek letter sigma. So Greek letter sigma. Now this is an uppercase sigma, and I'm going to do it really carefully. This is what the uppercase sigma looks like if you're being very careful about it. And this is the only time I'm going to be really careful about it, because generally sigmas degenerate to something that looks like this, which is a sideways W. That's how people mostly write it when they're writing sigmas in math and science and engineering technology. So we're just going to degenerate to that sideways W immediately, and let's look at our first example. So this is a capital sigma. Greek letters, much like our Roman alphabet, have uppercase and lowercase. The lowercase sigma is something that used in statistics a lot, and we're just going to use this uppercase one. So let us look at our first example of sigma notation. Now, the thing about sigma notation, which you really should bear in mind, is that it does look a little intimidating initially. So let's write one out. And then we're going to take it apart piece by piece. So we write the letter sigma, and then below it we're going to write n equals 1. On top of it we're going to write 4, the number 4. And then to the right in brackets we're going to write 3n plus 1. Now, if you haven't seen sigma notation before, this can be very confusing and intimidating. So we're going to take it apart step by step. The first thing we're going to notice is the index here. The variable for our index is n. Remember that the index is the subscript on each term. And this tells us that our starting index is 1. And it also tells us at the top that the final index is 4. And the part that's in brackets after the sigma, that gives us the value of the element. That may not be very illuminating, so I'll start writing this out. The way that I like to do it is I take the starting index, which is n is equal to 1, and I just write it above with a little circle around it. The circle is just to show me that that's not a number I'm considering, it's just showing me the number of the term, for example. And then I'm going to write a 2, because then n's going to be 2, n's going to be 3, and n's going to be 4. We're going to be adding all of these terms together because it's a sum. And now we take a look at the part that I've highlighted in blue here, the 3n plus 1. Notice that our first index has a value of 1. So then I'm going to write that 3n plus 1 is equal to 3 times 1 plus 1. That whole thing represents the first element with index of 1. Then we go to looking at our index of 2. If I take a look at my index of 2, then when I sub in 2 in 3n plus 1, I get 3 times 2 plus 1. Maybe that's a little easier to see if I just say times here. And then for my element, for my index of 3, I get 3 times 3 plus 1, and then my final index is 4, and I get 3 times 4 plus 1. So if I multiply these all out, or sorry, multiply and add, I'm going to get 4 plus 7 plus 10 plus 13. And of course I'm not done yet because I'm trying to find the sum. And when I add 4 plus 7, I get 11, and then 21, and then 34. So this complicated sigma is actually just equal to the number 34. So to recap, what I would recommend is that you write the indices at the top, starting from the first one and going up by 1 until you hit the last one. Figuring out the value of each term by plugging the index into the expression to the right of the sigma. Do a little bit of number crunching, and then come up with your answer. Let's do another example. And the instruction is going to be to evaluate. What this means is in math, you've got an expression that will actually have a value, and you're just supposed to crunch the numbers and come up with what that value is. So we're going to evaluate. Oh, let's just do the quick one. The sum from I equals 0 to 3 of 3 to the I. Once again, we're going to take a look. Our index now is I. Generally, the variables we use for that are I, J, K. L is not a good choice because it looks like a 1. M or N are totally fine. Please don't use O as a variable. That's also a terrible choice. But our index now for this particular problem is an I, and so we're going to have we're going to start with 0. Sorry, lost my my attention wandered for a sec. And then adding 1, you're going to get 1, and then 2, and then we're going to go up to 3. And so when I plug in I equals 0, I get 3 to the 0. When I is 1, I get 3 to the 1. When I is 2, I get 3 to the 2. And when I is 3, I get 3 to the 3. Simplifying, this is 1 plus 3, plus 9 plus 27. And that's going to give me 27 plus 3 is 30. So this is going to give me a total of 40. Let's do one last little example in which we take something. Let's just scroll up here. And let's write the following. In sigma notation. Now we're not actually going to try to find the sum, we're just going to try to rewrite it. So what if I have, for example, the sum 1/6 plus 1/7 plus 1/8 plus 1/9 ... and I want to write that in sigma notation. Well, the first thing we're going to do is we're going to write, here's an answer, we are going to write a sigma, which is a sideways W. And now we have to choose a letter that we're going to use for our index. I'm going to use M because I haven't used M yet. And our M is going to run from wherever we want for our starting position to our final term. Now notice that this is an infinite series because it does not stop. So no final term given. So this one's going to run all the way to infinity. So we're going to write an infinity at the top. And then you actually have some choice in where you want to do your starting index. If I want to be supremely lazy, then I would choose 6, because then my first term is just going to be 1 over 6 or 1 over m. And then when I increment, my next term would be 1 over 7, because my first m is going to be 6, my second m is going to be 7, my third m is going to be 8. And so I could write this sigma, in sigma notation, I could write this series as the sum from m equals 6 to infinity of 1 over m. But if I prefer, if I'm a traditionalist, I could also do the following. I could write the sum, and I could choose maybe k. I haven't used k yet, and let's say I really want to start from 1. This is still an infinite series, so I'm going to sum from k equals 1 to infinity. And now I have to write an expression that when I stick k in it, my first term will be 1 over 6. So it's going to have to be 1 over k plus 5, because when k is 1, I want 6 in the denominator, and then when k is 2, I want 7 in the denominator. And so I could also write the sum in the following manner. And in fact, I can start that wherever I want. I could start with, j is equal to 0 to infinity, and I could have 1 over j plus 6 instead. So there's multiple ways of writing this correctly in Sigma notation. And that's it.